Hey, welcome back, Calculus AB. This is actually a very cool lesson, and given that enthusiasm and excitement, you can probably tell, wisely enough, this is a very challenging lesson. I don't know, do we want to say difficult? I'm not ready to say difficult yet, but I'm going to say challenging. I wish I were doing this in person so I could, one, take your questions as we go, but two, be able to gauge your reaction and see how things are going. So I have some figures here that I want to show you. Would you agree that this is a circle on the base? Would you agree that this is also a circle on the base? Would you agree, though, that as I hold these up, they're quite different shapes? This one right here, I put it on top of my head. It kind of reminds me of the Pope hat, doesn't it? And this one, maybe Moana might use this to scrape fish. I don't know, right? I'll scrape them up towards you so you can see that. I'm not sure what the shapes are here. And the whole point, if you've learned anything today from this lesson, is it doesn't matter. These are quite different shapes. They all started out with the same circle base, right? But they're different, okay? So the first one I'm going to show you is good old Pope hat, but it's a different shape now because I've got bigger slices here, and I actually can take apart these slices. It's still a circle from the base, okay? But if I take it from the side, each of these cross sections, and that's what we're calling this, a cross section. I've sliced this up into a million bajillion, but this is big enough that I can actually hold, is a square. Okay, so I'm going to put that square right there. It has a thickness, and we're going to use calculus. You can probably guess what's going to happen with that, but we're going to find that volume. Here's the another one that comes apart of good old Moana's fish scraper here. Again, starts out with the base is a circle, but what's different is that each of these cross sections now, if I take one apart, this one is a triangle. Can you find the area of that square? Yes, you can. If you know this length of this side right here, because that's the side that fit into the base. So if I start putting it back together, here's my circle as we look at it from the top, right? Whoops, that's not my circle. Here's the rest of my circle right there. Okay, so if I could move this cross section into that, we would have a circular base. Okay, so if we look at that from the bottom again, our circle is complete. If we take this one slice out and turn it on its side and say, yep, I can figure out the area of that, it's a square. Same thing, let me reproduce our Moana's fish scraper here. Okay, there it is, looking at it from the top. Here it is, looking at it from the bottom. Okay, but could I take out just this one slice? Okay, because you can kind of see, and you can kind of see it from different sides, and ooh, ah, and ooh, it looks from the front like I don't know, a fish scraper. Who cares what it looks like? No. Can I take that one slice out and look at that as, yep, that's the area of a triangle, 1/2 base times height, and we can find that. Okay? If you understand that, and if you can get past the caring and worrying, because in years past people just can't do this until they see what it is. You don't care what the shape is, okay? As long as you can find the area of this, the area maybe of a semicircle, the area of a rectangle, etc. You can find the area of that cross section. We're going to use calculus to slice that up and find those. So now if we go back to these two shapes here, here's our Pope hat. You can kind of see, yep, each of those are squares. You can see each of those squares as they come, but it makes this looking, I mean, who knows what it looks like? Who knows? Who cares? Same idea here. If you look at it sideways, you can see each of those triangles smaller and smaller and smaller, and then it gets bigger towards the middle and then smaller again to taper off towards the other side. Okay? So if you get that, you should be okay. If you don't get that, you should still be okay. If you can't picture what it's looking like, that's really not the point. Now, there are problems in your book. I will either type up a worksheet and post that tomorrow for you to practice on, or assign some problems in my math lab. Newsflash, recently my math lab has been having some performance issues just because of the amount of traffic that's on. So it is what it is. So maybe I'll type up a quick worksheet and an answer key and get that for you. So let's try some. The base region, and we've seen that before, right? The region is bounded by y equals square root of x for 0 is less than x is less than 2. Okay? So all of these cross sections are going to fit the square root curve. All right? So that's what we're starting with. We're starting with the square root curve from 0 to 2. That's analogous to my base is a circle. I'm putting in a bunch of slices from radius this to that kind of thing. Okay? So we'll start with that. You'll see why I'm doing the square root curve in just a second because it'll be real handy. Let's do our first example. Find the volume, because now we're using volume, okay, of a solid with square cross sections. Now I don't know what that looks like. And I've got some ideas. I've got a teeny beeny square over here. I've got a bigger square, and as we go from 0 to 2, those squares are getting bigger, bigger, bigger. If you need to, think of a piece of, let's say, like cardboard or cardstock or index card or something like that, where I've got a tiny one that I'm cutting, a slightly bigger one, a slightly bigger one, a slightly bigger one, a slightly bigger one, as we go from 0 to 2. And let's draw in some representative rectangle at that point. And I'm going to give it a little thickness, 1 so you can see it, but 2 to remember that, oh yeah, we're calculating that width, dx, to be infinitely small. We're going to use calculus there. Okay? So this first one, I'm going to make an area here. And this red line represents that, just like I had my circular base, put it up here so we can see it, and pull out that one slice here. This red line is this edge right here. It's in my base, and I'm sliding it back in. Okay, so that will tell us the height of my rectangle, or the side of my square. Okay, and then we should be able to find the area of a square. Okay, so we've got one little individual square, so let's fill out the rest of our square. Even though we don't know what this looks like, maybe it's like a cornucopia, a modern looking cornucopia. Google that if you don't know what the word cornucopia is, with square edges on it. Don't know, don't care. I really don't, okay? Would you agree though that if, and I'll just draw this one, I'm not going to try to do this one, but I can do this one here. We should have a thickness, dx, and then I've got a square, that we can find the volume of that, right? This height is dx. This side here and this side here are going to be the same. So the height of all of our shapes, they're going to be prisms, rectangular prisms, is going to be dx, but the area of that is going to be volume. So volume equals side squared times dx. So really what I need, and this is the equation that you'll need here, volume equals the integral from such to such, from a to b or something like that, of the area times dx. And your job is to find the cross-section's area. Dx is going to give the thickness. I'm not going to try to draw this for each of our, because we're going to do a triangular cross-section, we're going to do a semicircular cross-section. Dx is always going to be the same, but if you look straight on that area, we can figure out, oh yeah, the area of that, volume equals the area times dx. And we're going to use the integral to accumulate all of those volumes from 0 to 2 in this case, because that's what our region stops at, from 0 to 2. Okay, so how would you find the height of this square? Because area is what we need to find for, and then we'll plug that into our volume equation. Well, isn't that just volume or area of a square? Isn't that side squared? Notice I'm not using x squared, because I want to find this. This area here is the side squared. Now, if you did the homework last time, I should be able to find this height is just s, isn't it? the height from the top of our curve down to the x-axis is just s. So I've got area equals side squared. Well, what is that? Well, the top is square root of x, the bottom is 0. So in this case, area equals square root of x squared. That just equals x. So our volume equals the area from 0 to 2 of what? A, which is x, dx. Okay? Any questions? I mean, this is where you need to be asking questions during office hours, or look at some videos, or email me, or try. I mean, this will be an uncomfortable lesson. I agree. That's okay. Maybe it's a blessing that this won't be on this year's AP test, but you know what? I still want you ready for next year. So we're going to go College Park ham and make sure that you can do this. So here you go. The setup is the hard part. So yes, use your calculators. I mean, if you want to evaluate this in your calculator right now, that's cool. I bet we could all do this, though. The fundamental theorem of calculus says take the antiderivative, 1/2 x squared, evaluate that bad boy from 0 to 2, and you get 1/2 2 squared minus 1/2 0 squared equals 2. And that's the volume of whatever that shape is with square cross sections. Again, I've got a teeny cross section of a square to a biggest one, and they're gradually getting bigger, 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 bigger. And all I need to do is figure out the area of that square. Let's try another example. This time, I'm going to find the same region for the base. But we want find the volume of the solid with equilateral triangle cross sections, or triangular cross sections. Triangular cross sections. Okay, so we're going to use that same region. In fact, we'll use the same region for all these examples. The same region, square root of x, but this time we've got cross sections that are equilateral triangles. So if you remember the Moana fish scraper, here, don't know how far I'll go. See what I did there? So I know how far you can go. If you just try these problems, you'll go far, or who knows how far you'll go. So I've got a square. Instead of a square, I've got a triangle that's a equilateral triangle. So I've still got this. I'm going to draw my region in again. It's the square root curve. But this time I'm drawing in my representative dx right here. But this time I'm sliding in a card from 0 to 2 in the shape. I'll make this big enough so we can all see it here. In the shape of an equilateral triangle. Equilateral triangle. Well, how are you going to find the area of an equilateral triangle? Because if we can do that, we can do our volume. Area of any old triangle is 1/2 base times height. Well, I need a base and a height here, so I'm going to drop that perpendicular. Now, pretend that this is an actual equilateral triangle. It should be a little more uniformly drawn, right? So if I know this, I've split my base in half, right? In fact, I might call this side S, and that means that this side is 1/2 S, using my 30, 60, 90 triangles, right? So if I kind of, maybe I'll draw this up here. This is going to be 60. This is 30. The side opposite, so if I call this S, the side opposite that 30-degree angle is 1/2 of that side. The smaller side is always going to be 1/2. And we split that in half. I think you all remember that. If we were to do Pythagorean Theorem, S squared equals 1/2 squared plus I don't know squared, and solve for I don't know squared, we should be able to get this, or you should remember this from geometry too. Square root of 3 over 2 S. That would give you that height there. Okay? So we derive that. 1/2 comes from that. Remember, B is this whole red length, so it's not 1/2 S. That just helped us get around to that square root of 3 side. So my B is S. My height here is square root of 3 over 2 times s, and you get square root of 3 over 4 s squared. That's the area of all equilateral triangles. If you just want to remember that, that would be good. That would be a great idea. So volume equals the integral from 0 to 2 of square root of 3 over 4. But what's our side? S squared, right? Well, isn't that red length still square root of x? So square root of x squared dx. Clean that up. Square root of 3 over 4 x dx. Okay? This is s squared, but remember, in this case, this will be the same. Square root of 3 over 4 s squared, that's true. In this special case, now you can see why I picked the square root of x as our function way at the beginning, because it made the squares go away, and it was easy. It was easy to integrate that. Okay? So the square root squared is just going to give us plain old x. That's where that's coming from. Okay? Do the same antiderivative. You get square root of 3 over 4 times 1/2 x squared from 0 to 2. And do that. I'll let you finish that up if you're not sure. Square root of 3 over 2. Square root of 3 over 2. All right? Let's try another one. Same region for the base. Not sure why. I don't know if you can hear it. It sounds like a helicopter flying overhead. Not sure what that is, but I'm just going to keep going because, yeah, it is what it is. With semicircular cross section. Semicircle. Okay, so same region. We've got y equals square root of x. From 0 is less than x is less than 2. And those are inclusive. But now, so let's draw that. Square root of x from 0 to 2. But now, here's my representative rectangle, so I'll make a nice bright red edge there. This red edge is going to slip right in there. But now I've got a bunch of semicircles. Okay? They're small, as in teeny, beeny, tiny, all the way up to this area here when the x value is 2. So you've got a little index card, a slightly bigger, slightly bigger, slightly bigger, as they increase to slide in to make a solid. Okay? What we're using is calculus to accumulate the volume, but if I can just find the area of just that thing. Okay? Well, what is the area of a semicircle? What is the area of a semicircle? The area of a whole circle is pi r squared. The area of a semicircle, 1/2 pi r squared. Be careful. This r is not the square root of x. Okay? In fact, this entire red length, just like it's been for the other two examples, is the square root of x. That's the diameter, so I need half of that. Right? That's your r right there. So to find the r, it's going to be area equals 1/2 pi. That comes from the equation. R is 1/2 of that. 1/2 of square root of x squared. So are I good with that? This 1/2 is always going to be there. Square root of x is going to depend on what that length is, but again, you can kind of see why. We're squaring that 1/2, so it would turn out to be 1/8 pi x is this one. This equation right here will work for all r's, okay? In our case, though, we had to figure out what r is in terms of that whole red length. It's going to be 0 to here. The radius here, when x is 2, right, is going to be 1/2 of the square root of 2. The dog likes this letter, okay? Any questions? Any questions? So think about that. So 1/8 of pi times x. Well, our volume is the integral from 0 to 2 of 1/8 pi x dx. So it's still the same one that we've done before. 1/8 pi times 1/2 x squared from 0 to 2. Plug things in, and you'd get 4, 1/2 of that, 2, 1/4 pi, and minus 0, so pi over 4 is your answer. Alrighty? So those are 3 examples, similar ones. The problems that I'm going to assign are out of the book. So if you've got your book handy, great. If you don't, I'll assign some problems and maybe make a worksheet. My math lab is kind of on the fritz, so be careful with that. And if you're wondering, I sent out a message. I did extend the deadline for my math lab, which was supposed to be due the night of 4/2, which is the day I'm recording this. This is actually the lesson for 4/3 though, because we hadn't done cross sections yet. So now you should be able to do those my math lab problems. So if you want to get some practice, go ahead and do those now. There's only a few, so that's probably the ones that I would be assigning. So maybe I'll assign type up a quick worksheet, or we'll kind of combine those into a lesson worksheet. I do have some worksheets at the end that will combine a lot of stuff. All right. So if you want to get some extra practice, this is in section 6.3 in your textbook, 7, 9, 10, 13. And maybe I'll work through a few of those problems next time. I'll make a videos with some more examples. All right. Sounds like enough for today. I hope everything's going well. And take care and talk to you soon. Have a good one.